Alright, we made it through rational, radical, and polynomial equations and inequalities, and now we're going to go into Chapter 3, and we're going to explore exponential and logarithmic functions. Exponential functions are things that we are familiar with. We've had them several instances back in Core 2 and Core 3, so we have some familiarity with those. Logarithmic functions, we briefly touched on those also in Core 3, and we'll get in much more detail and depth in our logarithmic section here. We have several different objectives that in Chapter 3 that we will do, but basically you can see them here. We're going to evaluate, analyze, and graph exponential and logarithmic functions. We're going to apply properties of logarithms that tie in directly with the properties of exponents. We have power rules, product rule, quotient rule. Those are going to tie in nicely with the exponential rules that are also rules for logarithms. We're going to be solving exponential and logarithmic equations, which is a really important key here. We're going to be able to algebraically solve exponential equations that we've never been able to do before by using their logarithmic counterparts, their inverse. The logarithms are inverses of exponents so that we can solve them. And finally, we're going to model exponential logarithmic data and find specific examples where we can apply it and make models and then make predictions from those models. So in this lesson 3.1, we have two main objectives, and that is to evaluate, analyze, and graph exponential functions. And then the second one is to solve problems involving exponential growth and decay. So again, hopefully we'll be fairly familiar with a lot of these concepts and try to brush up on those. In the first objective, a little bit of the history here, or a little lesson that they have. We've studied in Chapter 2 algebraic functions. Those were that we could be obtained by adding, subtracting, multiplying, and dividing. In this chapter, we're going to be looking at exponential logarithmics, and they're called transcendental functions because they can't be expressed in terms of the algebraic operations of addition, subtraction, multiplication, division. So in effect, they say they transcend algebra. They go beyond what we've already learned about algebra. The main point that we need to focus in on here is what makes it a power function versus what makes it an exponential function. Here's a good example. If it's going to be a power model, the exponent is a known power. This is a cubic function because the power is known. If we switch the roles of the base and the exponent around, the x is in the base, the 3 is in the power. If we change it around as it is in g of x, now we've created an exponential equation because now the variable is now in the exponent. So when we have a variable exponent and the base is known, these are called exponential functions. And they give you some examples of that in your text and your reading. I just placed them here so that you could look at them. The first thing that they're really concerned about is our ability to sketch graphs of these. Since we've had some exposure to these graphs, what we're going to do is we're going to go in here and we're going to talk about how we can sketch these graphs. We want to be able to sketch these without the use of technology so you can anticipate on your next assessment that you're going to be sketching these graphs without the use of a graphing tool, calculator, or computer. So in our first example, how do we graph an exponential equation that has f of x equals 6 to the negative x? Well, the first thing I'm thinking of, there's two different ways that you can kind of process information, and that is I could rewrite f of x in another way, another form or fashion. I could write it as 6 raised to the negative 1, then raised to the x, which means it's 6 or 1 over 6 raised to the x. And if that's the case, what we've learned in prior courses is that anytime the base of this exponent is a fraction or a number between 0 and 1, so if that base, I'll just call it b, is between 0 and 1, then we're going to have an exponential decay model. And a decay model always goes from high and goes to low. So in the back of my mind, I'm thinking I've got an exponential decay model. It's got to go from high to low. Now I just need to have some landmarks to hit. Okay, so that's one way to think about this one. The other way to think about this, and it's kind of a nice and it's a unique way of using our transformations that we learned, is we can go ahead and keep this as 6 raised to the x and then raised to the negative 1. Actually, that's not really kind of how I want to write that. What I want to be able to do is, if we have f of x equals 6 to the x, and if I know what that graph looks like, then I should know what the graph of x, 6 to the negative x looks like, because all I've done is we've changed the input. If you remember back to our transformations, if the only difference between a graph with a positive input for x versus a negative input for x is that this will be a reflection across the y-axis. So I'm trying to put a plug in for some prior learning that we did. If we replace x with a negative x, what that's going to do in effect to our graph is it's going to reflect across the y-axis. So I want to try that method here with you, and we're going to model that one. So if I just graphed f of x equals 6 to the x. And if I just use some relatively easy points, some good ones to use are, how about if x is a negative 1? If x is a negative 1, then that is 6 to the negative 1, and 6 to the negative 1 is 1/6. Put in a 0. Anything raised to the 0 power, or 6 to the 0, is equal to 1. And then if I put in a 1, 6 to the 1 is 6, so I get 6. So it gives me enough points to kind of locate where the pattern or the path of the graph is. So at a negative 1, it's got to be a 1/6, so it's hanging real close to the x-axis. For a 0, we get a 1. For an input of 1, we get a 6, so I got to go up here. And our graph would go along the x-axis and then up through the other 3 points of that graph. Now that's if I graph f at x equals 6 to the x. But if it's 6 to the negative x, now I talked about this negative x reflecting it across the y-axis. So if I reflect across the y-axis, the 0, 1 stays the same. Reflection across the y-axis is going to take this 1/6, it's going to reflect it across, it's going to be negative 1/6. It'll take this order pair, negative 1/1/6, and it'll reflect it across, and it'll be 1/1/6. So in essence, our graph would look like this. Now that's using that transformation idea that we talked about when we put a negative value for x. We can graph these 6 to the x, then come back and say reflect across the y-axis, and we have the shape of our graph. So the green graph is our final graph that we want to look at. I can come back and I can explain that in the other way as well. The other way to look at this is using your flexibility of exponent rules. This is 6 raised to the negative x, which is the same thing as saying this is 6 raised to the negative 1 raised to the x, which is the same thing as 1/6 raised to the x. And now you can test your points for x and f at x, and you're going to get very similar results to what we just talked about. If you put in a negative 1 for x, negative 1 is going to reciprocate the base. We're going to get a 6. You put in a 0. Anything raised to 0 power is 1. You put in a 1, and you're going to get 1/6. And you're going to model the exact same points we have over here. So I'm giving you a couple of different options here on how to graph. But the main point is that we're able to graph exponential growth and decay models without the use of technology by using a few specified points to get us the basic shape of the graph. And the other thing that we should be familiar with is that these exponential graphs, unless we have vertical shifts up and down, have a horizontal asymptote at y equals 0. No matter what we put in for x, we can never get a value that is equal to 0 or less than 0. And now they're going to discuss the domain, range, and all the other things that they asked to talk about. So the domain. For every exponential function, it's all real numbers. I'm going to use the most convenient and simplest way to write these answers. I'm not going to go to integral notation. I'm just going to put whatever's easy. All real numbers. The range on this, the range, to me, the easiest way to represent that is I could use integral notation. It's got to be greater than 0, don't include 0, so parentheses 0 all the way up to positive infinity. Or if you wanted to, all your y values have to be greater than 0. X-intercepts and y-intercepts. Are there any x-intercepts on this graph? Shouldn't be unless we have a vertical shift up and down. So on our particular graph, there are no x-intercepts, so there's none. The y-intercept on our particular graph has to be the order pair 0, 1. Asymptotic behavior, we only have one horizontal asymptote, and that is where y is equal to 0. There are no vertical asymptotes, so none. The end behavior, as x approaches a positive infinity, our green graph is approaching 0. As x approaches a negative infinity, our green graph is approaching positive infinity. And then finally, they ask you questions about whether it's increasing or decreasing. Our graph, we're looking at a green graph, we're going to read it from left to right. It's decreasing over the entire interval, so it's increasing over the set of all real numbers. Or if you'd like, I guess I can always come back to this interval notation from a negative infinity to positive infinity. And then it's decreasing nowhere, so never would be a good response. Okay, so that's the first brush up on that. Now we're going to look at the second graph. And just to show you, I had a graph here that showed you the actual graph that I put on a calculator or graphing calculator or computer, and that's what it looked like. So just to show you that it's not too far off. Next one, reverse roles on these guys here. We have an exponential equation. I know immediately that it's exponential growth because the base is 5. Anytime that base is greater than 1, If that base is greater than 1, it's got to be a growth. And anytime it's a growth, it has to go from low to high. So I already have in the back of my mind what this graph is going to look like. There's nothing real tricky or special about this one. We've put in a couple of maybe 3 points to help us locate. I always like a -1, 0, and 1. They're pretty easy to deal with. If you take 5 to the -1, 5 to the -1 is the same thing as 1/5. Remember, negative exponents reciprocate your base. It flips it. So reciprocate your base. If it's a 0, 5 to the 0 is 1. Anything to the 0 power is 1. And then 5 to the first is 5. So simply we're going to put in our ordered pairs. 1, 5. We've got 0, 1. And we also have -1, 1/5. We have this vertical or horizontal asymptote along our x-axis. It's coming up through our ordered pairs that we've already plotted. That's the path of our graph. So now at this point, what they're asked us to do is come back and answer these questions about domain, range, and x-intercepts, and so on. So very quickly, a quick discussion on this. The domain of this, the domain is going to be all real numbers. The range is going to be all real numbers greater or equal to 0. So I'm just going to say y has to be greater than 0. The x-intercepts, we have one x-intercept. It's at, x-intercepts. There are no x-intercepts. I was getting ahead of myself, so there's none. Y-intercept is again at the ordered pair, 0, 1. Horizontal asymptote is still at the same location. It's still along our x-axis at y equals 0. There's none or no vertical asymptote. The end behavior on this one, how about as x approaches a positive infinity? As x approaches a positive infinity, our graph is going towards positive infinity. As x approaches a negative infinity, our graph is approaching 0. Our graph is always increasing, so it's increasing over the entire domain of real numbers, and it is never decreasing. Okay, that's the second one, and just again, I plotted this graph so that you could see how closely we can just sketch those versus having to do the whole thing in the calculator and try to emulate that. So again, the important part is, keep in mind we're going to have a non-graphing calculator section on your quiz or assessment, so therefore I need you to be able to get these graphs written in or plotted without a lot of technology. Okay, the final graph that we have here is h of x equals 1/4 raised to the x plus 1. Okay, so some clues that I'm picking up here. The base of this is in between 0 and 1. Anytime it's in between 0 and 1, it's got to be exponential decay, so it's going to be falling. The other clue that I have here is that we have a vertical translation. This is going to shift our graph 1 unit upward. Okay, so we got to deal with this. So the first thing I'm going to do is I'm just going to graph our parent function in this one, which is 1/4 raised to the x. So I'm looking at some input-outputs on these. So x, and then this is h at x. So what if I put in a -1, a 0, and a 1? Those are good test points again. If we put in a -1, a fourth to a -1 reciprocates that base, so it basically gives you a 4. Anything to the 0 power is 1, and then we put in a 1, we get 1/4. Now, that's not the only thing we have to do that. We have to add a 1, so as soon as we add a 1, it's going to vertically shift everything up. So it's going to become a 5, a 2, and this is going to be a 1 1/4. So those are the ordered pairs that we're going to graph. So the ordered pair, -1, 5, so -1 up 5. Our ordered pair is 0, 2. Our ordered pair 1, 1 1/4, so 1 and then 1 1/4. It's going to be right around in there. Okay, so one of the other things that is a key characteristic of every exponential graph is the location of the horizontal asymptote. In the last two examples, our horizontal asymptote has been on the x-axis or at y equals 0. But as soon as we do a vertical translation, we're moving everything up on our graph up 1 unit, which also means we move up our horizontal asymptote. So that's going to give us another feature that we need in order to graph this exponential function correctly. So it's coming from high to low, sweeping down. It's going to go right along our horizontal asymptote at y equals 1. So this got changed not from y equals 0. We have to add 1 because of the vertical shift, so it's at y equals 1. And we'll fill out the rest of the data here on the side. The domain is going to be all real numbers. The range, now because we shifted our entire graph up 1, the range changed now. Now the y's have to go from greater than 1. It's no longer 0. They're always going to be bigger than 1. The x-intercepts, there are no x-intercepts. The y-intercept, has gotten changed. All the others have been at 0, 1. Now this one got moved up. Now it's at 0, 2. Horizontal asymptote is now y equals 1. There's no vertical asymptote. The end behavior, the limit as x approaches a positive infinity. Now our values approach 1, so they get closer and closer to 1. The limit as x approaches negative infinity goes to positive infinity. This graph is never increasing. It is always decreasing. It's always going downhill, so that's over the set of all real numbers, or from a negative infinity to infinity. So in this first section, what we're supposed to do is we're supposed to learn the shapes of the graph, basically the different patterns of those graphs. And I wanted to show you here again just how good you can get your graphs just with a quick sketch. So just verifying that as the graph and give me some more graphical evidence. So shapes of these, increasing or decreasing based on whether it's a growth or decay. The growth and decay is determined by the base, and they've got some different variations here when they put in negative exponents. Don't let that throw you off. We've got a couple ways to attack that now.